Welcome back. In Part 1, Acme Support was the smallest honest agent, a model with instructions, run by runner, with no tools and one direct text reply. That was useful because the boundary was visible. The agent could say hello as Acme, but it could not check orders or issue refunds. Today we keep the same customer support task and remove the agent loop. You will see what happens when normal Python code owns the route, and the model is only one step inside that route. Start with the plain version first. It gives every later design choice a standard to beat, instead of letting complexity sneak in early. A customer asks for a refund, and the system has one job: turn that message into a useful support response. Keep that concrete case in mind. Here, Python owns the route. The model labels the message, then if and else branches choose what happens next. Later agent features have to justify themselves against this baseline. Extra flexibility is not free when fixed code already works. Lock this in. When the structure is stable, a workflow is the design to beat. Agents earn their place only after the route stops staying simple. A support request can move through a system in two very different ways. The useful question is who picks the next action. On the workflow side, your code is the controller. The model helps with one label, but Python decides the next branch. On the agent side, the model becomes the controller. It decides what to call, then receives the result and decides again. Both designs produce a final answer. The difference is the path taken before that final answer appears. Think of this like a train track versus a driver. The workflow follows fixed rails. The agent steers at each turn until it is done. Now isolate the left side. The route is fixed, visible, and easy to audit before any agent behavior enters the lesson. First, the customer message arrives. For example, Acme gets a refund request for order 8,821, not a vague abstract prompt. Second, the model classifies the message. Its job is narrow: return one label, not decide the whole support process. Third, that label becomes data for Python. In the provided run, the label is refund, so the refund branch is eligible. Finally, normal if, elif, and else logic picks the reply. Debugging starts by checking which branch Python selected. Now look at the other side. The next step is chosen during execution, not fully written as branches ahead of time. The run starts with the customer message. Think of it as handing the case to a worker, not sending it down a fixed belt. The model chooses what to call next. That is the key shift. Routing moves from your branches into the model loop. The runtime executes the chosen action and returns a result. Without that runtime layer, the model would only talk about actions. The result feeds back until the loop reaches final output. That power matters later, but today we measure it against simple code. Think of the classifier like a receptionist who only writes one sticky note: refund, shipping, product, or other. In lesson_02_workflow_version.py, classify_intent uses OpenAI, calls client.responses.create, pins model equals GPT-5 mini, and asks for one label. The important part is the narrow contract. The LLM sees the customer message, but it does not route the case. If the label is wrong, inspect this prompt and the raw output first. Now the steering wheel moves into respond. This function is deliberately hard-coded. Refund returns the refund desk message, shipping points to /orders, product points to /catalog, and anything else gets a short fallback. That is why this is a workflow, not an agent. The routing is visible, testable, and boring. The fix for a wrong CAN message is simple. Change the matching branch. Before running, map the file at a beginner level. We need the pieces, not a giant dump of every line. The file starts by loading configuration. Load_dotenv makes the local API key available before the OpenAI client is created. OpenAI creates the client used by the classifier. If the key is missing, this is the layer to check first. Classify_intent returns only the label. That narrow output is what keeps the workflow easy to reason about. Respond maps the label to a CAN message. This is where policy wording and routing choices actually sit. Main supplies the concrete example. Order 8821 asks for a refund. Then the file prints intent and reply. A tiny terminal proof is enough here. We only need to see that the input became a routed answer. Run the exact command. Python lesson_02_workflow_version.py. That file name is the learner-facing artifact for this lesson. The first output line is intent refund. That proves the classifier understood the customer request as a refund case. The second line is the workflow reply. Because the intent is refund, Python chooses the refund desk message with a 3-day processing promise. The result has two halves. First, a model labels the request, then fixed code selects the message. Intent is the model side evidence. If this says product for a refund request, fix the classifier prompt first. Reply is the Python side evidence. If intent is refund, but the answer is wrong, inspect respond. The 3 days wording is fixed policy text in the branch. The model is not inventing that promise at runtime. Use this debugging rule. Check the label, then check the branch. That split is the biggest practical benefit of this workflow baseline. The first warning sign is growth pressure. When real cases keep arriving, a tidy branch list stops staying tidy. Brittleness starts with partial refund. The request is reasonable, but the existing refund branch is too coarse, so respond needs a new branch. Exchange instead creates the same pressure. The workflow can handle it, but only after someone writes another route. By turn 30, the team is rewriting respond weekly. That is not a model failure. It is a routing shape failure. Here is the fix rule. When branch growth becomes weekly work, pilot an agent for adaptive control. Do not switch earlier just because agents sound exciting. The second warning hides in the contract. Two pieces must agree on the same set of names. The classifier knows the allowed labels. If it learns a new label, that new name becomes part of the contract. The responder knows the matching branches. If it does not know the new label, the route falls into the fallback. A fifth label exposes the coupling. For example, Exchange can classify correctly and still fail because no branch exists. The maintenance rule is direct. When labels change, update classification and routing together. Otherwise, one file silently outruns the other. Now turn the lesson into a reusable choice. The safest design is the simplest one that matches the shape. Stable structure belongs in code. If the order of steps and routes stay predictable, workflow wins. Changing structure raises cost. New edge cases, policy variants, and route names make the branch list harder to maintain. Agentic control has to earn it. The extra loop is justified only when fixed routing stops matching the work. The decision rule is simple. Start deterministic when the shape is predictable. Add an agent only when the task demands adaptive control. The next part turns today's contrast into a scoring check for Acme support. The first trigger is complex decisions. Refund judgment changes when loyalty, exceptions, and edge cases affect the answer. The second trigger is brittle rules. If policy changes sit in spreadsheets, hard-coded routing becomes expensive to keep aligned. The third trigger is unstructured data. Free text messages, photos, and PDFs are harder to force through fixed branches. In part 3, should you build an agent? The 3 triggers, we turn this into a score. 0 means stay deterministic.